Okay, children, we're going to start with number 3, which is ridiculously easy. Your x is wrapped up in a natural log, and then that's wrapped up in another natural log, and it equals 1.5. So first we work from the outside in to get to our x. We have to undo the natural log, and the inverse of that is the exponential function e. So we put these up as exponents, and that cancels, and we get log x equals e to the 1.5. Now that's kind of a strange number, so you might want to change it to a familiar decimal and use an approximation. So approximately that. Now we have another log to undo, so again we use the inverse function. And we get that canceling, and we have x equals e to the 4.4816 approximately. I should use approximately, I guess. And if you put that into your calculator, you get 88.384 approximately. End of story. Easy problem. Okay, this is number 7, and again we have a single log on this side, so we can undo it with the anti-log, which in this case would be a base 10. And so that undoes itself, and we get 2x squared minus 3x equals 10 to the 2, which is 100. Bring that over to one side, and we have a simple quadratic that won't factor, unfortunately. So we use the quadratic formula, 3 plus or minus the square root of 9 minus 4ac, which is negative 100. So you're going to end up with 809 under there, over 2 times a. And when you put that into your calculator, you get two answers, approximately 7.861. And the other one is a negative, which might worry you a little bit. Ought to worry you a tiny bit. But when you check them, because of the squaring and subtracting, turns out both of these numbers make this equal 100. And log base 10 of 100 is 2, and therefore they both check. So they're both correct answers. Okay, this one is number 11a, and you should recognize this just as the third law of logs that says log any base of x to the n is n times that log of x. This is base e. By the way, I'll be saying log when it's base e, even though technically I should say natural log. We always just say log in calculus because that's the one we use. So if I say log, you got to look and see if it's natural log or the common log. Now, otherwise, I'll say the base. So this is always true, because it's just the third law. However, it's only true when defined, and in this case, x has to be positive. You can't take the log of 0 or the log of a negative, and so your final answer is all real numbers greater than 0. All right, log, this one, 11b, it is different because it's not x that's cubed, it's the log that's cubed. So it doesn't mean log of xxx, it means log of x times log of x times log of x. So at first glance you might want to say, well, this is silly, it's not true. But there might be individual numbers that work. So I'm going to use a Jedi math trick, which allows me to replace an expression with a single variable. And that gives me z cubed equals 3z. Bring the 3z over. Factor out a z, and we get 3 answers. Oh, this is equal to 0, by the way. We get z equals 0, root 3, or negative root 3. And we're not taking the log of these numbers because these aren't your x's. These are your z numbers. So that means log of x can equal any of these 3 numbers. And logs can equal a negative. Here's a graph of log. The value of the log can be negative. What you're taking the log of can't be negative. So then to figure out what x is, we need to undo the natural log, and that's the exponential function e. And so x is going to equal e to the 0, e to the root 3, or e to the negative root 3. So those are your 3 answers, and those are all perfectly fine. This one means 1 over e to the root 3. So it's a reciprocal of this one. Oh, and this one's just 1. So I don't know why I would write e to the 0. That's kind of silly. Let's make that a 1. Alrighty, this is number 15, which is kind of pathetically easy because exponential 7 and log base 7 are inverses. So all of this just equals 2x. Well, now when is 2x equal to 2x? Always. Except this is only defined if you can take the log of 2x in the first place. So 2x has to be positive, which means x has to be greater than 0, and that's your answer. By the way, if you want to do this in interval notation, it would be 0 to infinity. Alrighty, number 19 is kind of cool. It's very different. Now all these natural logs might mess you up, so let's change log 4 to an approximate decimal. And let's use z for log x again, natural log. And then I think you'll see how to apply your algebra skills. Multiply both sides by z. Distribute on this side because you're multiplying over a sum or a difference. Difference, sum, same thing. Just adding a negative when you have a difference. And now we have, I guess I should use approximately here, shouldn't I? Because it's not exactly equal. And then let's move everything to the right so that my z squared can be positive. Oops. 8. Nice number, huh? That'll be a plus because I'm moving everything to this side. Okay, I don't think we can factor that, so we use the quadratic formula, 1.3863 plus or minus 1.3863 squared minus, 4ac, which is the same as b, over 2a. Now, luckily or unluckily, depending on how you look at it, when you put what's under the square root into your calculator, it comes out negative. What does that mean? That means we'd only have imaginary answers, and we're not going to do logs of imaginary numbers, not in this course anyway. So our answer is the empty set, no solution. Okay, number 23 is another easy one. Well, at least to start off, it's easy. We have a single log on this side, so again, the exponential function that matches will undo it. It's its inverse. When you apply inverses, you just get back what you started with, which in this case is x plus 3 over x minus 1. Now 16 to the 1/2 means the square root of 16, which I hope you know is 4. Cross multiplying, we have an easy algebra problem here. 4x minus 4, don't forget to distribute. Subtract x from both sides, add 4 to both sides, and x is simply 7/3. Is that going to be all right with our log? We can't take the log of a negative or 0. Yep, 7/3 plus 3 is positive, 7/3 minus 1 is positive, so we're good to go. That's the answer. Okay, this one's number 27, and this time we're going to use our Jedi math trick a little bit more forcefully. We're going to let z equal e to the x, and we're going to let e to the negative x then equal 1 over z. That way we turn a pre-calc exponential problem equation into a simple algebra problem, because now we've got z minus 1 over z equaling 1. And then it's straightforward. We multiply by z, we get z squared minus 1 equals z. Bring everything to the left. And then this doesn't factor, so we use the quadratic formula, 1 plus or minus the square root of 1, and then that'll be plus 4, so we end up with the square root of 5 over 2. But now this time, z is e to the x, and e to the x is always positive. That's always positive. And so there's no way we're going to get 1 minus the square root of 5. So we're only going to use the one with the plus sign. So now we have z, which is e to the x, equaling 1 plus root 5 over 2. So to solve for x, we've got to get rid of the e. What's the inverse of exponential e? It's natural log. So we take the natural log of both sides, and then our final answer is 1 plus root 5 over 2. Now you guys that are going to be engineers, go ahead and type that into your calculator, get an approximation, but I'm just fine. I'm just happy as punch with that answer. Number 31. Now, this time we have got a couple of log 6s. So you can't put a big 6 and then distribute it, because they're not multiplying by 6. You're raising the entire side as exponents with a big 6 as the base. So what we have to do before we can undo the logs is combine them so that we just have 1. And so we're going to use our first law of logs to rewrite this as log base 6 of x times x plus 1. And now we can do the inverse by applying the anti-log function, which is a exponential 6. So now that cancels out, they undo each other, and you end up with what's inside. 6 to the 1 is 6. X squared plus x equals 6. Bring the 6 over. You know what, I'm going to need that space there, so let me just do that all in one step if you don't mind. X squared plus x minus 6, and luckily this one factors because I'm really tired of that quadratic formula sometimes, you know. I like it when it factors nicely. Now this time we are taking the log of the x values, so x can equal 2, that's going to work just fine, but x equal negative 3, no, because you can't take the log of that negative number. So our answer is just x equal 2. Okay, so this one, number 35, is the same situation as the last one. We got a couple logs here. Can't undo them until we combine them as one, and then we can rip it off with a big 10, because this is the common log base 10. So we're going to have 2x plus 4 times x minus 2 equal 1. That's our first law of logs. And then we can undo it with the anti-log. The anti-log common log is big 10. That cancels. Now when we multiply this out, you might have noticed this was 2 times x minus 2, plus 2. So it's going to be difference of squares times 2. So when we multiply it out, we get 2x squared. We get plus 4x minus 4x. That's gone, and that's not a surprise. And then minus 8. And that equals 10 to the 1, which is 10. Now, whoever planned this problem did a good job, because when we add the 8 and divide by 2, we get a nice 9. So x equals 3 or negative 3, because negative 3 squared is also 9. However, again, we get the issue with logs only being able to act upon positives, so the negative 3 is not going to work. Final answer, x equals 3. Okay, this time we have a log on each side, but this 2 is in the way. We can't put a 10 here and cancel because the 2 is in between them, so that won't work. So the first thing we got to do is jump that 2 up using the third law of logs. And so that's going to be x minus 1, the quantity squared. The whole argument inside the log has to be squared. Now, if the log of this equals log of this, obviously the arguments have to be equal. I don't even need to write that 10. Or you can think of it as anti-logging. It's up to you. And while I'm at it, I'm going to go ahead and square this out since space is an issue here. All right, let's bring everything to the right. I'm not sure why I kept the parentheses. X squared minus 3x. Oh, and the 1 cancels. Cool. That equals 0. So then we can factor out an x. And we get x equals 0 and x equals 3. Let's see, is 0 going to work? Be okay here, but 0 is not going to work here because we can't take the log of negative 1. Therefore, that one's extraneous, and our answer is 3. Okay, now we're getting into the tough stuff because we don't have all numbers. We get this y here. We want to solve for x in terms of y and all, whatever other numbers are around. And we got x's over here, and we got x's over here. We got to get them together if we're going to solve for them. Now, we can't use the inverse log because of this minus y. It doesn't have a log on it. We can't combine it. So what we're going to do is we're going to get that y out of there, bring the log family together so that we can combine them. So we'll put the y over here, and then we'll have log x minus log of 3x minus 1. Now I can combine them, okay? So that's going to be log of x over 3x minus 1 according to the second law of logs. But I still have to get x out of there to solve for it. So we're going to do the anti-log on both sides, and that'll give me x over 3x minus 1 equals 10 to the y. And don't worry about this being complicated. Just pretend it's a number. What would you do if it was a number? You would multiply by this, so do the same thing. 10y times 3x minus 10y. Now I'm running out of room here. So I'm going to go up here in a second. But again, we're solving for x, and now we've got x's on both sides again. So I've got to get the x's on the same side. I'm going to move the 10 to the y over here because I'd like to keep that positive. And then that'll be 10 to the y times 3x minus x on this side. Okay? So then all I got to do is hop that x out, factor it out. And so I'm going to come on up here. That'll give me 10 to the y equals x times 3 times 10 to the y. I like that 3 in front better. Minus 1. And so now all I can do is divide by this. And I get a pretty silly looking answer, but nevertheless, that is the correct answer to this problem. Okay? So now we've solved for x in terms of y, and that's what we were asked to do. Okay, now we're getting into the inequalities, and remember that e to the x and log x are both increasing, as is any log or exponential function as long as the base is greater than 1. And so what that means is that order is preserved. In other words, if x gets bigger, so does y in both cases because they're increasing. So that means we can apply inverse functions, either logs or exponentials, and the order will stay the same, so we don't have to worry about switching that. All right, so with that said, let's divide by 4 because that's on the outside of everything. That would be the last thing you did if you were evaluating with x. First you'd e it, then you'd subtract from 10, and then you'd multiply by 4. So going backwards, we're going to divide by 4 first and then work backwards. So now we're going to subtract 10. And let's just change that to a decimal. Be a little easier. And then if we multiply by -1, that does invert the equal sign, the inequality sign. And then we just take the log of both sides, which will not invert the inequality sign. And so the log and the exponential are inverses, and we're done. If you want to change that to an approximate decimal, I don't know how to write an approximate inequality sign. Would you do something like that? X is approximately greater than or equal to 2.375. I'm joking about that. There really is no symbol for that. You would just have to lie. All right, so that's that first inequality one. All right, another inequality, and as I said before, the natural log is an increasing function. So if I take the natural log of both sides, I maintain the order. Oops, that should be plus x. Sorry about that. Oops, that's not going to work. Yuck. And so that's going to be greater than or equal to the log of 100. Oh, maybe I should have taken the, you know what, the common log also. Well, no, because common log is going to be good on that side, but it's not going to be particularly good on this side. So I'll just stick with the natural log. So then the 2 plus x can come down in front according to the third law of logs. And then you've got log e, but that's just 1, so I'm not even going to write that. And now all we have to do is subtract 2. So it's log of 1, natural log of 100 minus 2. And if you want to change that to a decimal, knock yourself out. Okay, continuing with our inequalities, again, the exponential 2 to the x is an increasing function, so if I apply the anti-log of 2 to both sides, I'm not going to change the order. So I'm still going to have 2x minus 1 over x minus 2, but this time 2 to the 0 is 1. Now, this one you can't solve algebraically. You can't multiply by x minus 2 because we don't know if it's negative or positive. We could make two cases, one where x is bigger than 2, one where x is less. That gets really messy, so we're not going to do that. Instead, we're going to bring the 1 over, and we're going to make it into x minus 2 over x minus 2 so that we have a common denominator. And that'll give me 2x minus x, which is x, negative 1 minus negative 2, which is positive 1, over x minus 2 is less than 0. Okay, so that function we could actually graph because we know how to do that, or we could use a number line. I think I'll use a number line. And so it's undefined at 2, this quantity, and it's 0 at -1. So we'll put the -1 there, obviously, and the 2 here. And now we're going to check numbers. So like, for example, at -3, let's say, we'd get -3 plus 1 over -3 minus 2. And then at 0, which is in this interval, we get 1 over -2. And then in this interval, let's try a 3. That would give us 4 over 1. Now we want less than 0. Less. So that's negative. Okay? This is positive. This is positive. So the only negative is right here. So our answer are all the numbers between -1 and 2. There it is in interval notation. If you prefer, you can write it in algebraic notation. Another inequality where we can apply the natural log. Again, that's an increasing function, so we do not have to switch the inequality sign. So we take the log of 1. Ooh, and that's 0. That's good. Here we just get 1 over x minus 1. Kind of like the last one, we need a common denominator, so that's going to be 1 minus x over x. Change the 1 into x over x. And for our number line, we're going to split it 0 and 1, because 0 makes it undefined, the quantity, and 1 makes the quantity 0. If I try -1, I'm going to get 2 over -1. If I try a half, 1 minus a half is a half over a half. And if I try, say, 2 over here, any number will work, -1 over 2. So we want positive this time, greater than 0. We want our quantity to be positive. And so that's where that's happening. So again, our answer is in the middle there. And if you prefer, you can write it that way. X is between 0 and 1. Okay, this looks like kind of a long one, doesn't it? But they're all base 2, praise the Lord. And so we can combine them all using our handy-dandy law of logs. We've got x times x plus 1, but then the log that's being subtracted is a divisor. I'm going to hop that 2 out of there just for the heck of it. I don't know if I'll need that or not. But there we go. All right, now we can do the anti-log. This time it's exponential function 2 to the x, or 2 to the y, or 2 to the whatever, to undo the log of 2. And we get x times x plus 1 over 2x plus 3 is less than 1. Oh dear. So now we got to bring that over. And so we're going to have x squared plus x. I want to put the 2x plus 6 back, unfortunately. Subtract 1, written as 2x plus 6 over 2x plus 6. And that's going to be less than 0. And so, let's see, we're going to have x squared plus x minus 2x is minus x. And then minus 6. Don't forget to distribute your negatives. All over 2 times x plus 3 less than 0. And that factors x minus 3. Oh, I was scared that was going to cancel and then we'd have a hole. How do we deal with that? Don't have to worry about it. Not in this problem. And so let's do this a little differently. Let's graph it. This is a rational function. Let's let y equal this whole thing, in other words. We've got a 0 at 3, and a 0 at -2, and an asymptote at -3. And our end behavior would be x squared over 2x, which is just x over 2. So when x is big, so is y. So we're going to come this way. All the powers are odd, so we're going to go through. And then we're going to go through, and then we're going to have a sign change and go to the other side. Oh, wait a minute, that's not working. Oh, yeah, it is. I can't go through, so I have to turn around and go back down. All right, so I'm looking for where we are negative, and so that's going to be this part from -infinity to -3, and from, where else are we negative? From -2 to 3. Boy, that was a tough one. It's the final answer. Oh, but wait a minute. We can't use negatives. Oh, so the only part of this we can use is 0 to 3. So forget that. Our final answer is x is between 0 and 3. Okay, this is number 67, and I rewrote this to show you that this part is the third law, because it's x squared, so the 2 can come down. The log of a power is that power times the log of x. But this one is not, because this is not x squared. This is log of x times log of x. So we're going to use our Jedi math trick and let z equal log x, because that's going to give me 3z squared minus 2z minus 8 equals 0. Now that happens to factor. It took me a little while to factor, but it's 3z plus 4 times z minus 2 equals 0. And so we get z equals negative 4/3 or 2. But what does z equal? Z equals log x. Can log x be a negative? Certainly. Log can be a negative. Can't take the log of a negative, but the log can be a negative. So we have log x equal negative 4/3, or the natural log of x equal 2, and then we anti-log it with a exponential function. That gives me x equals e to the negative 4/3, or e squared. So we get 2 answers. Okay, this one we're to solve for x in terms of all this other stuff, alpha and beta. So we need to get x by itself, so we're going to move log beta over. Since it doesn't have an x in it, we need to put it on the other side. And then alpha is multiplying this, so let's divide both sides by alpha. We get negative log beta over alpha, and then all we got to do is take the anti-log. But now I just had a thought. Why don't we rewrite this as negative 1 over alpha, oops, that's not a very good alpha, times log of beta, because then I can jump this up as an exponent, can't I? So now I've got log x equals log beta to the negative 1 over alpha. Okay, so if log of x equals log of that, then x is just whatever's in there, right? Does that make sense? There you go. So now I'm done. I was about to make this harder on myself. Alrighty, so again we're solving for x without numbers but with letters instead. And this is looking like the logistic function, isn't it? So we solve for x, that would be solving for time in terms of all the other stuff, carrying capacity, blah, blah, blah. So anyway, we're going to start off by cross multiplying because fractions are really hard to deal with. And then anything that's not got an x in it has to go to the other side. This is just weird. Divide by by. Bye-bye, by. And then take the natural log of both sides. I'm running out of room here. And divide by negative k, or I guess we could make that negative 1 over k in the front there. Let's see, I'm going to have to write kind of small here. Negative 1 over k times the natural log of a minus y over by. Sometimes it's hard, to know exactly how much simplifying they want. We could bring that up. We could leave it there. No. If we bring it up, the negative will flip this. Bring it up and make it an exponent, and the k would be the kth root. So I'm thinking I'm going to like it like this. Kth root, and then the negative 1 flips it. I don't know. What do you think? You like it like that, or do you like it better the way it was? Okay, my battery's about to run out. This is going to be the last one. I did 87. It's really long, but it's very, very cute. So I'm going to leave that for you, and if you don't know how to do it, call Lydia. She can do it, I bet you. So we're going to undo the log base pi, which looks weird and scary, but it turns out it doesn't really matter because that undoes it. And then what's left doesn't have a pi in it. But I'm going to have pumpkin pie tomorrow. Then we undo the log base 4 with exponential 4. And again, that doesn't change the order because 4 to the x is an increasing function. Piece of cake now. Move the 5 over. And then that means x is between 3 and negative 3. But wait! we have to keep this positive. This is the tricky part. We have to keep what's inside this original log positive. And so x squared has to be greater than 5, which means x is greater than root 5 or less than negative root 5. And so we can't use this whole thing. We end up going from negative 3 to negative root 5, and then from root 5 to 3. So we have this really bizarre answer, but nevertheless, when you put all the requirements together, that's what you get. Bye-bye.